Hello, my name is Moses Washington, and today I'll be talking about X-ray fluorescent spectroscopy using the EA1000A3 as well as the EA1000VX, as they have similar specs. What is XRF and how does it work exactly? X-ray fluorescent spectroscopy is a non-destructive technique used to both qualify and quantify the elemental compositions of different materials. It's typically used for measuring film thickness and composition, the general elemental quantification and identification of most materials. The identification of specific metal alloys is its most common use, and a less common use is trace level analysis in solid or liquid samples, as more efficient models of analysis are available, such as HPLC, atomic absorption spectroscopy, and so on. To the right, I have a basic diagram of X-ray fluorescent spectroscopy and its setup, where an X-ray source shoots X-rays onto the sample. They're deflected into a detector as X-ray fluorescence, read by the spectrometer and funneled into our computer for analysis. How does this happen, and what are some of the inner workings of X-ray fluorescent spectroscopy? If we know anything about electromagnetic radiation, we know that X-rays have the power to disturb the inner workings of atoms. So we use this understanding, and X-rays are used to excite the sample, causing the emission of electrons or fluorescent X-rays from the sample, which have energetic characteristics of the elements which are present. When an inner electron is removed by an energetic photon from the X-ray source, an electron from the outer shell drops into its place. This can happen in 3 different transitions. Our measurement comes from these transitions because each transition yields a fluorescent photon with the characteristic energy which is equal to the difference of the initial and the final orbital. We can characterize this understanding by Planck's law, which tells us that the fluorescent radiation is equal to Planck's constant multiplied by the speed of light divided by the energy, which is equal to the difference in the initial and final orbital. The 3 different transitions that can happen are an L to K transition called a K alpha transition, an M to K transition called a K beta transition, and an M to L transition called an L alpha transition, but is its least common orbital shift. How is the instrument set up? Well, we have an E-gun as our X-ray source, which shoots our X-rays into an anode. The deceleration of the electrons when the anode is hit causes a broad X-ray continuum to be emitted. This is known as breaking radiation. That breaking radiation is then redirected into a monochromator, which takes our wavelength band and narrows it for redirection into our sample, which the X-rays then go into the electron and cause the electron, which go into the atom and cause an electron to be emitted, which give off fluorescent X-rays, which are directed into our detector for analysis on our computers. To our right in the figure, we can see the potential corresponding positions of elements and their associated energies on the x-axis. The y-axis is a quantification of how much of each element is in the sample. So our EA1000A3 and VX. Let's talk about those a little bit. Specs are that it's able to analyze solids, liquids, and powders, though powders must be prepared in an aqueous solution. Our source is a small air-cooled X-ray tube powered by 50 volts and a circuit of 1000 milliamps or microamps. It uses a silicone semiconductor detector. Has a chamber size of 1, 3, and 5 millimeters, which is auto-changeable. A 5 auto mode switching filter for different intensities of X-ray. The max sample size is 370 by 320 by 120 millimeters, and the instrument size is 520 by 600 by 445 millimeters, weighing only 60 kilograms and needing only 200 volts of AC power. Some of the key capabilities are high-speed measurement, an analysis line conversion function, material identification function for comparison of recordings to industry standards, as well as the example, as well as a 6 sample changer shown on the right. So what is our connection to chemistry? It's a material. It works in the field of material science. It does elemental chemical analysis, both qualitative and quantitative. It requires pre-concentration or the creation of standards as well as dilutions for the appropriate analysis. It is a spectroscopy tool, and data analytics is involved. And where is this tool distinct from other tools we use at DePaul University? It's similar in the fact that we use solids, liquid, and powders for our other analysis. It is a qualitative and quantitative chemical analysis. We currently use spectroscopy in the form of IR spectroscopy, NMR spectroscopy, and atomic absorption spectroscopy. Pre-concentration is necessary in our other evaluations, and the use of anodes and a monochromator are also uses that are taught here in our analytical classes at DePaul. But where does it differ? Here are sources of X-ray. Our signal is fluorescent photoelectrons and the qualification and quantification of those. It is a non-destructive process, unlike atomic absorption spectroscopy. It's not currently being used at DePaul, and the experimental technique and applications of X-ray fluorescent spectroscopy are different, which is why I think it would be good to have this tool here. So thank you guys for listening, and here are my references.